everybody hear me? No, oh, sorry. Here, it's better.
Okay, our last speaker is George Karakalias, and he will be talking about GADT pattern matching.
Thank you very much. I would like to talk to you about my work with Tom Shrivers, Dimitris Vitiniotis, and Simon Payton-Jones on reasoning about pattern matching in the presence of GADTs. Well, this involves mainly two things. Check exhaustiveness, that is, check if pattern matching covers all cases, and also redundancy, that is to check whether all equations in a pattern match construct have accessible right-hand side. Since we wanted to do this in Haskell, also we want to take into account laziness and see how this affects the above checks. And also, well, I won't have time to talk about this in the talk, but we also managed to reason about more exotic features like view patterns or pattern synonyms, etc. Well, for an example, here you have zip, variation of zip that pairs element-wise two lists. The problem with this function is that it has only two clauses. It assumes that the input lists will have the same length, which is not expressed in the type system. So if we call this function on two lists of different length, like here, we get a runtime error. What we would like to have and what we do have is a warning like this one, which says that zip is not exhaustive. There are two things that, there are two possible calls which will make it crash at runtime. Now, since we intended to use zip on lists of the same length, we can now do this using GADTs and express this invariant at the type level by having vectors, by using the same type variable n, which expresses exactly this, that both input arguments and also the result will have the exact same length. Now, the problem with this is that GHC gives us still the same warning, and as you can see, both cases indicated as not matched are actually ill-typed, unfortunately. What most programmers do is a catch-all case, like here, which is a bad thing to cover actually nothing. And the problem is that GHC gives us no warning whatsoever for it either, which means that the redundancy checker is also broken. Yes. A bit about laziness. Actually, I didn't expect this to be so important, but during the work we saw something strange. Here we have a contrived example, but I think it's obvious that the second clause is completely overlapped by the first one. And that's why GHC, for this definition, gives us this warning, which says that the second one is overlapped. Well, since we have no other warning for redundancy by GHC, this warning used to be a synonym for the second clause is redundant. But actually it's not, because if we call f with undefined and false, we get an exception. And this happens because we try to match the first clause, we fail because false cannot unify with true. But then while trying to match the second clause, we have to evaluate the first argument, so we crash. If instead we remove it, we get a 3, which means that even though the second clause seems to be overlapped by the first one, it's not actually redundant. And if we remove it, we change the semantics of the program. Instead, what we propose and we have implemented right now is a different warning in this case that says that the second clause, it may have an inaccessible right-hand side. Now, we'll never get a 2. But this doesn't mean that it's redundant. So what we did is that we designed an algorithm that handles GADTs, guards, and laziness in a uniform way by abstract interpretation of pattern matching. I'm not going to say a lot about this, but I would like to focus about the representation, the abstraction of clauses. Instead of abstracting over clauses using patterns like we did before, now we constrain them by using delta, which is a set of constraints. Since we want to reason about all these three things, delta includes type constraints, term constraints, but also strictness annotations. And the structure of the algorithm goes as follows. It's incremental. First of all, we abstract over all possible values, and then we process each clause separately. the notion of a clause, well, I tend to think about it like a partition function. If you think about all possible values, a clause partitions them into 3 different categories. Some of them can match the clause and will give us the right-hand side. Some of them will not match, so we'll have to go on and try the next clause. But some of them may diverge while trying to match. Well, this is the processing of the first clause, but instead of returning this, we pass the uncovered set from the first clause to the next one, and we do this until the end. Obviously, the final uncovered set is what hasn't been covered by the whole match. Now, all these covered, divergent, and uncovered sets abstract over sets of values, but they are too relaxed. So, in order to be more precise, after this, we want to filter out, to make them smaller, by checking delta for non-satisfiable constraints. And since we have 3 different types of constraints, we can rely on 3 different solvers, which is highly modular. Well, how to interpret the results? If both the covered and the uncovered set are empty, this means that the clause is actually redundant, and we can safely remove it. If the covered set is empty, but the divergent is not, it means that we'll never get the right-hand side, but this clause forces some arguments, so it just has an inaccessible right-hand side, but cannot be removed. The other 2 cases are just useful, so we make no warning whatsoever. And for the uncovered set, well, if it's non-empty, this means that there are cases that are not covered, so we issue non-exhaustive warning. Otherwise, our function is total. I won't get into much detail, but if we see this example, what we would expect the algorithm to do here, we would expect to see that this function is, first of all, exhaustive, but also to be able to detect that the last clause is redundant. So I abstract over all possible values using 2 variables that can unify with anything. I omit many constraints here because I didn't have enough space. But if we see only the type level constraints, the covered set looks like this. A has to be unified with the n and b as well, and this means that n has to be equal to 0 because of the first pattern, and n has also be equal to 0 because of the second one. Now the divergence set looks something like this, which is quite intuitive because we may diverge while trying to match either if the first argument diverges or if the first argument is an anneal, so we match against the first one, but we fail and diverge while trying to match against the second argument. Finally, the uncovered set looks like this. Either the first one is not empty, or the first list is empty and the second is not. Well, if you see the constraints here, the last clause has a non-satisfiable set of constraints, which we can rule out by our type oracle. So we continue with the rest. Here. Yes. After this, we also have a set of inconsistent type constraints, which we can also remove, which means that the final set of uncovered only after checking the first 2 clauses is already empty. So the match is exhaustive. Now, because the set is empty, while trying to check the last clause, all sets are empty, which means that both the covered and the divergent set are empty, so it is considered redundant. And all is good. Well, there's much more. There's no time, but you should check the paper. There's a lot of stuff about the guards, the full pattern translation, and the implementation of the core language, of the core function. There are many motivating examples, a correctness theorem, and also tons and tons of related work. Now I would like to talk a bit about the implementation. Sorry, I guess this didn't happen. We made it happen. Thank you very much. Well, we have implemented our approach in GHC. Well, the lines of code are not really precise, I'm still working on it, but you can already download and play with it. I plan to merge it before the end of the month. We managed to solve several bug reports. Actually, the first 4 and the second 5. But also because we have now already the framework set, I think that it's pretty easy to implement solutions for the other ones as well. The solvers we used are, first of all, for type constraints outside in X, GATT's existing type inference engine, which makes it consistent with the behavior of the type checker. And for the other ones, I wrote a minimal solver, well, to do at least what we had before and maybe better in some cases. Also, we wanted to check our resolve. What this table means? Well, we tried to compile several packages and get about many numbers. Because there have been many complaints since 2006 when GADTs were first implemented, I think Simon Peyton-Jones implemented 2 patches to improve a bit the algorithm, but both of them were ad hoc. So I named here GHC1, GHC without these patches, GHC2, GHC with these patches, which is the current head, and new, our implementation. As you can see, these patches were quite effective. They managed to reduce the warnings in half. M represents the false warnings about missing cases, that is, false non-exhaustive warnings we got. So the patches managed to reduce them to half, and we managed to do the same. Unfortunately, we don't have a 0 because of the term solver, which is not pretty strong at the moment, but we're thinking about improving it in the future. Also, we counted the redundancy warnings we wanted to have, but we didn't get. And as you can see here, both GHC before the patches and afterwards have no results. But we managed to find 38 cases, redundant clauses that weren't issued before. About performance, well, instead of counting time, we thought that it would be better to check the sizes of the sets that we generate, covered, divergent, and uncovered. As you can see here, over 99% of them had size less than 100, apart from 5 disturbing cases, which all look like this. What happens in this case is that we have quadratic number of cases, and there were 5 pattern matches on the same data type, which had 54 different data constructors, which gave rise to over 3,000 different cases. Well, it's not our problem exactly, it's the problem itself. It's proven to be undecidable, it's proven to be NP-complete anyway. So, well, in summary, we designed and implemented a uniform framework to reason about pattern matching with GADTs, guards, and laziness. The key idea was to do abstract interpretation of pattern matching, and the algorithm is quite modular in constraint solving. We also managed to close several bug reports, and even though not discussed, it seems to play well with the rest of GATC's features. Like I told you before, there are tons of related work. And for the future, we would like to see if we can maybe plug in some external solver for the term equality so that we can get better results. Well, it's undecidable in the general case, but see what we can do. And also, it would be nice to apply the same algorithm to the restricted setting of closed type families. Thank you very much.
This is very cool. I only asked this question because I encountered it recently. In the presence of OR patterns, you can have a clause that is only partially redundant in the sense that you, the programmer, has written down a bit of pattern that really doesn't contribute at all, but nor can you just delete the entire match.
Yes.
Do you handle that in any particular way, or?
Well, in Haskell, we don't have OR patterns, but if I treat it, there are many possible transformations that could give you the right result. Well, the implementation, the sets we use, we represent missing vectors as a tree because usually they have a common prefix.
Right.
So we could just split and have two possible paths, and we could give more specific results about just the part of the guard or the pattern in this case.
Mm-hmm.
No, we don't have it at the moment, but I think it's simple to do.
Okay, I have a question. How does this interact with data kinds? Does that improve your messages?
Yes, it works fine. Well, there's no problem with it. We just have to, like we generate type equalities, we also wanted to generate kind equalities, which weren't really supported until now, but Richard is working on it. So it was a bit ad hoc until now, but now it will work okay, I guess, now that we have proper kind equalities. We generate kind equalities, type equalities, and term equalities as well. Right.
So what's your plan for dealing with view patterns?
Well, you should check the paper about that. Because we have so many features, syntactic features, we had to extend the pattern language, so we allow pattern guards to be interleaved with the patterns now. So this makes it able to express, for example, if you say f of not to true, for example, this means that you pattern match against the variable x, and you also have a constraint that not x has to match with true. Right.
So you have a little, I guess your simplifier can do simple reductions?
Yes. Actually, yes. If you check this example here, these are quite different because of the order. You don't want the check to happen afterwards. You want it to happen before pattern matching against the second argument. So our current pattern language also has guards in the middle of the clauses. So we can have interleaved checks and the qualities amongst pattern matching.
Thanks.
Okay, let's thank George again.